Okay, the problem 2 says, wait, is it? An archer weighing 100 pound, an anchor weighing 100 pound in water is attached to a chain weighing 5 pound per feet in water. Find the work done to haul the anchor and chain to the surface of the water from a depth of 20 feet.
All right, we'll pull the chain and the anchor from a depth of 20 feet. Okay, so the anchor is going to stay at 20 pounds for its entire trip up the well. It's the chain that's going to change in its weight. So we're going to figure out the total work done. Let's see, let's put the top of the well here.
Oh, it's not a well, it's just water and surface.
Okay, so let's put that on surface. There's the surface. We've got this chain. And we've got 20 feet here. Let's put the y-axis of y is equals 0 here. Good morning. Morning. It's not cold out there. Tell everybody it's not cold out. It's fine. And our room it's ever toasty comfort. Okay, so we're going to do 2 things here to compute this work. This is a fixed force moving a fixed distance, and then the chain is going to be a variable force moving the distance. So for a fixed force, we just multiply the pounds with feet. So write that as work is equal to the work for the anchor plus the work for the chain. And so the work for the anchor is just going to be force of 100 pounds times the distance of 20 feet. Now to get the work for the chain, we have to imagine the chain to be cut up in tiny pieces. So here's one delta y length of chain, so that's delta y feet of chains. And if it's 5 pounds per feet, the force acting on that little bitty slice is essentially constant. It will be 5 pounds per feet times delta y feet. So here the force is 5 times delta y. Then we measure the distance that small piece of chain has to move. It has to move from this y coordinate up to 20 feet. So the distance there is 20 minus y. And then we do those slices over the length of the chain from y is equal to 0 to y is equal to 20. We've got our chain length here. And then our force is 5 times delta y. Delta y becomes the dy when the Riemann sum becomes the integral. And then the distance that the chain moves, 20 minus y. So again, force times distance. So the anchor was just like the problem where I lifted the back of the chain up before. That doesn't change its weight all the way up. So 20 times 100 is going to be 2,000 foot-pounds of work for the anchor. And then here I can pull out the 5 and get 20y minus y squared over 2 from 0 to 20. That's equal to 2,000 plus 20 times 20 will give me 400. 20 squared is 400, but divided by 2 is 200. So that gives me 200. 200 times 5 is 1,000. So there's a total of 3,000 foot-pounds of work. Now, it's really good. Propped up the camera against the thing. Will that work? You don't have to hold it. So we can see. Yeah, that works fine.
Yeah, you work.
And you don't have to hold it.
Yeah, that works.
Good. Well, $1 million worth of equipment. What else? What else you guys got? Think all of y'all stay good. At least turn on your camera so I can see you sitting there in bed and your pajamas on. Did we finish talking about fluid force? The two examples on the sheet of fluid force with the triangular plate and the rectangular plate with the water.
Well, we are dealing with a spherical tank,
Okay,
and well, you told me it is tucked in a grow.
okay, right. So that one was one we couldn't integrate. But the one I put on Webwork was some version of a plate, the coordinates.
It's something like a spherical, it's something like a spherical. It is not a whole other. It's leaving you know what
Yeah, I'm just gonna try to step you up. I want to make it work.
Thanks.
Okay, so let's look at a fluid force anyway. So let's take a plate that is shaped like this. Let's put it up, this is a right angle now. And let's submerge it in a liquid so that the total depth of the liquid is, I don't know, it's 10. So let's make this 5 feet here and 12 feet. Looks like it, 12 feet, let's put that. Make that 15 feet. Not bad. So let's find the force of water at 60.4 pounds per cubic feet. Find the hydrostatic force acting on this plate. If it is submerged. Submerged. In water. 62.4 pounds. So the idea here was that the force varies based upon the location of a point, and the force acting on this plate was equal to the product of the density. We're going to cut this plate up into little tiny strips, so we compute the area of each strip. The distance from the top that strip is. And then we set that up as an integral. So I'm going to put this on a coordinate system where the base of that triangle, or the vertex of that triangle, corresponds to the origin. And the y-axis is here. And this is the point 012. This is the point 015. And this is the point 50. Then we put a small vertical strip in there. along the y-axis, say here. And we need the area of that strip, which will be the length of that strip times the thickness of that strip, which is delta y. That's going to go here. It'll be our length times delta y. The distance is the same as the way we figure distance in pumping water from that strip to the top. So here the distance is 15 minus y. And then the density was the 62.4. The numbers on the integral sign represent the cuts that we made through the strip, or through the triangle, so our cuts are going to go from 0 to 12. The length of that strip we find just the way we did it when we found the length of that strip in area. It would be right graph minus left graph. So we just need to write the equation of the line that passes through the ordered pairs 0, 12, and 5, 0. So the slope is going to be 12 minus 0 over 0 minus 5. So our slope is a negative 12/5. The y-intercept is 12. So we use y is equal to mx plus b. Negative 12/5 x plus 12. But we need everything in terms of the variable y. So I'm going to take this equation now and solve it for x in terms of y. So I'm going to swap places with these two entities. Put the 12/5 x over here, subtract y. And then multiply everything by 5 over 12. And so the equation of that line over there is x is equal to 5 minus 5 over 12y. So the length of the strip is that right graph minus the left graph, which is just x is 0. And now our integral will look like the integral 0 to 12, 62.4, that length. Sorry? Backwards, I swap places.
Negative 12.
No, because I divided by that. So when I divide, I put it on. Right? Okay, so there's my L, 5 minus 5 over 12y. Then I've got 15 minus y, and then the dy. Then we'll just leave it right there. This is just polynomial multiplication, then integrate term by term. So this is force, so this is going to be units of pounds. So your book writes it as density times the area of the strip times the distance times dy. Or length of the strip, think about the length. See, the length of the strip times dy is the area, and then the distance is h. That's what you're going to use. Rho L H dy, but I write it out in words. I did make a formula sheet for all of chapter 6, and I've got a review for the test, which is, by the way, one week from today. Today is the 11th, 10th?
11th.
So 1, 7 plus 11 is 18. It's going to be over chapter 6.
Just chapter 6.
Yeah, just chapter 6. So I'm going to put a review sheet on Blackboard.
What are we going to learn later after chapter 6?
Yeah, we'll start that today. We'll learn how to integrate.
Oh,
Oh, we don't know that area yet?
Well, don't know how to integrate much.
Okay.
We're gonna integrate beyond the old UVU substitution.
oh,
Oh, no, I don't want
Oh, yes, you do.
to.
Oh, yes, you do.
so the one we are supposed to use for sphere question that we saw yesterday.
So there's a review sheet on Blackboard for chapter 6, and there's also going to be a formula sheet. I don't think I've posted it yet, but I will when I post. But the formula sheet is for you to learn, not use. I'm not going to set formulas to go fast. That's standard for you to remember. The last thing we need to do in this section is to compute something called center of mass. So unless anybody has any more questions, we'll finish center of mass. Good. This is part 3 of section 6.3. This is something you're going to use all the time in your mechanical engineering classes. You want to build something that's going to level. Make sure you have things that are well balanced.
I'm a biology major.
I know, you're just doing this as again, the pacing thing. When I talk to my doctor, he always tells me the hardest class to ever have is Cal 2. And I think, but watch this, my doctor. Okay, so when we talk about the center of mass, we're imagining a very thin piece of material that we'll call a lamina. And this lamina, we're going to place on the XY plane. We'll place it on the XY plane so that we have a top graph and a bottom graph.
Lamina?
Yes,
Oh, is it LA?
lamina,
LA.
LA,
Okay, okay.
lamina. Some thin piece of material. So here's my thin piece of lamina. It can have variable density. There might be a point over here with a greater density, and a point over here, and a point over there. But that makes the calculus part a little bit messier. So in this section, we're going to assume that this thin plate has uniform density. Good morning.
So are we assuming that the thin lamina has any thickness?
The thickness isn't going to matter to us, because that's where I'm. The thickness would provide the density.
Oh,
So
okay.
we're going to make it thin enough that we're not worried about the density.
Okay.
Right, now, if we did have to worry about the density, then we could just throw in another variable and integrate in another dimension. So we can do it with other calculus. But we're just going to assume now that the density is constant. Okay, so consider a thin lamina, let's assume that the density, any point is a constant. And we're going to use the Greek letter rho for density. Now there are examples where we could write rho as a function of x. So the density might be such that the density at any point might be directly related to its distance from the origin, or its distance from the x-axis or y-axis. Then you can formulate a term to go in here. All it is going to do is kludgy up the integration, but the integrals are all going to look the same. Now, if this plate were something that I could put on my finger, then there's one point on that plate that serves as its balance point. That if I put my finger on that exact balance point, it'll stay right there without even having to spin it like a basketball. If I'm on the balance point, I can hold it. But if I'm anywhere off of the balance point, that plate is going to want to fall off of my finger. So if I have my X and Y axes here, there's a tendency for that plate to want to go this way, and there's a tendency for that plate to want to go that way. We're going to call those tendencies to want to revolve in the horizontal and the vertical direction the moments of inertia. We're going to have a moment of inertia with respect to the x-axis, so the plate wants to fall that way, or the moment of inertia with the y-axis. Moments, inertia, present tendency of this plate to flip about either axis. Its desire to flip about the y-axis will be called the moment with respect to y. Here's my with respect to. I take out all the words, just do RT. We're going to denote that capital M subscripted with the y. Morning. And then we have a moment with respect to the x-axis. And that's going to be down.
What is WRT?
With respect to.
Oh, with respect to, okay, gotcha.
Those moments are going to play a role in trying to find the center of mass. Each moment is based upon a distance that that particular point is from the X or Y axis. And so we've got an infinite number of points. What we're going to do is cut this thing up into a bunch of little rectangles by subdividing the x-axis up. We're going to take all of these rectangles here. We're going to find the center of mass of each rectangle, and then we'll average them up and get the center of mass for the entire lamina. When you average something, you divide by the total. When I cut this up into rectangles, the total is essentially the area. But now when we take the area and multiply it with the density, what do we get? What's the product of area times density called? Physics?
You mean mass?
It is, it's mass. So when we compute these moments and divide them by the total mass of the region, we'll get the centroid. So first we'll look at the mass of the region. Mass is equal to area times the density. We'll denote mass with a lowercase m. I denoted density with that Greek letter rho, and we know we can find the area with a single integral. So the mass is just the integral of the density times the area. In our picture, it'll be the top graph minus the bottom graph. If the density is not constant, we keep it in here. It would be some function of x in calculus 1. If we had several variable calculus, this with a double integral and include a function of y. If it's a constant, we can pull it out. But I'll just write it in here for the most general case. So what we're going to do is compute each of these moments, divide them by the mass, and we'll get the center of mass, the average point or the balance point of that lamina. The moments are all based upon distances. If I take, say, the kth rectangle, and I want to find the center of mass of this kth rectangle, we would call that, say, xk and yk as that center of mass. The Lemon is the rectangle is gonna be so thin, and there's gonna be one central point to that thin place. We're gonna measure the distance from the y-axis to that arbitrary point, this distance here, and then multiply it with the area. Well, the area of this rectangle here is just gonna be top function minus bottom function. So we compute this moment by taking that length times that length. Well, this depends on where the rectangle is. It's going to move wherever the x is. So in general, that's going to be an x between A and B. That makes the moment with respect to the y-axis look like the product of that distance from the y-axis times the area of that rectangle. We make those Riemann sums, and then when we make those Riemann sums, this becomes a definite interval. When we want to find the moment with respect to the y-axis, we have to measure where that center point is for each rectangle, with respect to the x-axis, in this direction. So for each rectangle that's going to move to wherever the center of that rectangle is, these rectangles are infinitely thin, so I'm measuring the average of the two y values that bound the rectangle. I average two numbers by adding them and dividing by 2. So this length is going to be the average y value times the area. So we'll have the average y value, that'll be top graph plus the bottom graph divided by 2 times the area, which is top graph minus bottom graph dx. Up here, I forgot the density. Each one of these has a density term in it. So for me, that's the easy way to remember that formula, average y times area times density. But your book will multiply this out. They'll take this factor of 1/2 out front. And then what do you get when you take f plus g and multiply it with f minus g? You get f squared minus g squared. So this is the way you'll see it in the book with the density term right there. Again, density is going to be constant for us, so we can pull it out. But then to get that center of mass, denote the center of mass x bar, y bar, it's an ordered pair, the balance point. Usually we use that bar to denote an average, so that's essentially what it is. We take the average of all the x directions and the average of all the y directions. So it's the ratios of my divided by mass and the moment with respect to the x-axis divided by mass. It'll be an ordered pair that lies in this region, but again, it allows me to balance with each one. So 3 more formulas for you. Look at the ones that are on our sheet. There it is. All right, the first example, we have the graph of y is equal to 1 over x squared. Bounds the top of the region, the x-axis bounds the bottom one, and 2 vertical lines, x is 1 and x is 4. Picture will be up here. 1 over x squared will be kind of steep hyperbola. And we'll put a bound at x is 1. And x is equal to 4. From this point, that point. So it's kind of looks thicker there at the beginning. It gets real close to the x-axis more than what I've drawn. But it looks like that if I had to balance this on my finger, I would need to probably put my finger somewhere around here. So it'll be maybe something close to 2 in the x direction. This point here, my graph is way out of scale. That's the ordered pair 1, 1. That's the ordered pair 1, 1/16, since that's the graph of 1 over x squared. So my guess is that my center of mass is going to be have as its ordered pair something close to 2, and then some number smaller than 1.
Is it 416?
Oh, that is important. I also said in this problem, take the density just to be 1. This is going to be constant, this is going to be 0. So let's find these 3 integrals. Find the mass first, which is just the area. Find the moments with respect to the y-axis, moments with respect to the x-axis. So let's get the mass first. This is the area integral. So we're integrating from 1 to 4. Our bottom graph is 0, so we're just integrating 1 over x squared. And then integrate 1 over x squared, you write that as x to the negative 2. Add 1 to the power, and divide by the new power. So when I add 1, I get x to the negative 1, divided by negative 1. So I'm just going to write that as negative 1 over x. 1 to 4. And so we get a negative 1/4. Minus and minus is be plus 1. So the mass of that region is 3/4. So that number. Now for the moment with respect to the y-axis. The density is going to be 1, so I'm just going to put my integral sign here. That's the chance of the integral sign there. A to B, you take the distance from the y-axis times the height of that strip. That makes it the area of that strip. Distance from the y-axis times the area of the strip. So again, our g of x is 0. We're integrating from 1 to 4. And f of x was 1 over x squared. And so when we multiply that out, we get 1 over x. Doesn't do me any good to write that as x to the negative 1 and try power rule. What's the integral of 1 over x? That's a natural log of x. So we get the natural log of 4, because the natural log of 1 is just 0. Now we're ready to do this one. I use it in this form. Again, our bottom graph is 0. So all we have to integrate is 1 over x squared all squared times a half. At the moment, with respect to the x-axis, has a 1/2 here, the density is 1, and then f squared minus g squared, g is 0. We're going to integrate from 1 to 4, 1 over x squared squared. So that's x to the negative 4. Integrate that, I get x to the negative 3 divided by negative 3. Negative 3 is on the bottom. So I'm going to put it together with the 1/2 and get a negative 1/6. Then I need to evaluate 1 over x cubed from 1 to 4. So I have a negative 1/6 times 4 cubed is 64. I said it was negative. No, it's not negative. And then 1 over 1 is 1. So that's 63 over 64 times a negative 1/6. I could probably reduce that a little bit. Both of those are divisible by 3. Divide that by 3 and I get 21. And so I get, it could be negative. That's negative. One side negative. So negative times a negative is a positive. 21 over 2 times 64 is 128. That one is the next. So that number as the numerators in my x bar and y bar, and then our 3/4 is the denominator. And so in our example, r y divided by mass, and that was a natural log of 4. Mass is 3/4. So we get 4, natural log of 4 over 3. Y bar is the other one, and x divided by m. And x was the negative, oh no, sorry, negative 21 over 128. Divided by 3/4. Let's see, 3 goes into 21 7 times, 4 goes into 128 32 times. So it's the ordered pair 4, L 4, 3, 7 over 32. That's the balance point, that little funky shape right there. Good. All right, let's do the next example then. We'll take the formulas off, write them up for each problem. Let's see here. Next example says we've got a plate whose shape looks like the first quadrant portion of the region bounded by y is equal to 3x squared and y is equal to 1. Y use 1 instead of a multiple. Yeah, we're taking density to be 1. In the first quadrant, I got a parabola opening upward. Then y is equal to 1 here. So let's go ahead and get this point of intersection. I know y is 1 there. We're going to need that x coordinate. So we're going to set those two equal to one another. Then we get 3x squared is equal to 1. So x squared is 1/3. So x is 1 over the square root of 3. That always makes for nice limits of integration, doesn't it? We could fix that if you want. We change it to a 12. If that's a 12, and that's a 4, and then that makes x is 2. I don't want to mess with funky numbers, so let's go with whole numbers. Change this line to line was equal to 12. So then I intersected 212, and I could use 2 as my upper limit of integration. So it looks like this one's a little bit top heavy, but the balance point might be somewhere in here. So we're going to anticipate the x is a number a little bit bigger than 1, and the y is a number probably bigger than 10. I always like to guess, just makes the rest of the calculations that much. Okay, so let's get the mass of that region. Mass in our example is just going to be area, since the density is 1. We're putting strips in there, so my vertical strips will all hit the horizontal line on the top and the parabola on the bottom. So my f of x is the line y is equal to 12, and my g of x is y is equal to 3x squared. The density is 1, I'll leave it off. We'll have 12 minus 3x squared in here. And then we integrate over the range of the x's from 0 to 2. So we get 12x minus x cubed from 0 to 2. 2 times 12 is 24, 2 cubed is 8. That's 16. So that's our mass of that region. Hang on to that number. That's going to be the denominator. We find the center of mass. Then I like to do them in this order. I like to find the moment with respect to the y. So that represents the distance from the y-axis times the area of the strip. I'm saying it that way to help you remember the formula. So in this example, when we said we're integrating from 0 to 2, we've got the x here, and then top graph minus bottom graph. And so I multiply that out before I integrate. Got 1 to 12. Yep, we did. So that's, change that to a 12, but that's how we got the x's too. Oh, we changed that one to a 12. That one. Yes. Now I'm with you. Okay, so multiply that out and get 12x minus 3x cubed. Then we integrate. What is that going to give me? 6x squared minus 3/4 x to the 4th, 0 to 2. So I have 4 times 6 is 24. 2 to the 4th is 16. 16 divided by 4 is 4. So 3 times 4 is 12. So this one just gives me 12. Okay, a little bit more over here. Here's the formula for the average distance from the x-axis times the area. So we've got that 1/2 placed out front, 0 to 2, 12 squared minus 3x squared squared. Top graph squared minus the bottom graph squared. So I need to integrate 144 minus 9x to the 4. And I will get 144 times x minus 9/5 x to the 5th. Two times 144 is 288. 2 to the 5th is 32. 32 times 9, 288. Well, let's see, if I just think of this as 5 times 288 over 5 minus 1 times 288 over 5, I'll get 4 times 288 over 5. Then I multiply that by half. And so that gives me 2 times 288 over 5, 576 over 5. And look, that's 10-ish. So let's now set those numbers up in the numerators. Of the 16, we get our center of mass. X bar as the moment with respect to the y-axis divided by mass. That was my first number. That was 12. Mass was 16. So I get 3/4 here. The y-coordinate of the center of mass has the moment with respect to the x-axis divided by the mass. So that's 576 divided by 5, divided by 16. That's 576 divided by 5 times 16. Oh, I don't know. Do we need to reuse? I'm not so keen on it anymore. Or goes into both of those.
It's 36. Oh, wait.
This simplifies all together?
Ah, never mind.
No?
I just divided by 2.
I think this goes 144 times 4. Gives me 144. And that's also divisible by 4. So 3 times 4 is 12. Times 8 is 24. There's my y bar. 38 over 5, my x bar is 3/4. So 38 over 5 was 7-ish. Oops, I changed that. That's where that was going to fit in there. So there's the x bar of 3/4. That's 2, so that's 1. 3/4 is about here. 30 over 5 was 7-ish. I'm going to say our center of mass is here. That's pretty good. If you have a region that has a constant density and is, say, for instance, symmetric to the y-axis, then one of those coordinates is going to be 0. Which one? The region is symmetric to the y-axis. When I give you on web work, might be something like this. Then you would expect x bar to be 0, right? And then you just have to find the y bar. So we'll put that on the web work. Saves your calculations. It's easy formulas to use. Sometimes a little bit tedious. Like if I gave you a binomial here, you'd have to square binomials. So you can get icky steps. What's my examples? When they started, I think we had just mixed them. So your test 1 week from today, you start with areas of regions. So the important thing there is to get the graph to see if you need one integral and that it's horizontally or vertically simple, or if it's not a simple region, then you need 2 integrals. Then in the next section, we did the volumes by slicing. So we had either slices that were described as circles or semicircles, squares, or equilateral triangles. And the idea was volume is area times thickness. Then we did the revolution, solids of revolution by washers and shells. And then in 6.3, we changed things to polar coordinates. So graphic polar coordinates, find intersections, find areas. Then in 6.4, we did arc lengths, both in rectangular coordinates and polar coordinates. So a couple formulas to remember there. And then in 6.5, we did the work done on a variable force, like pulling that chain up. Work done on a spring with Hooke's law. Work done in pumping liquid from a tank. Fluid force. And now this. Are y'all good with that? I got all that organized on the review sheet with some practice problems. And some of the solutions might even be right on the practice problems. And I really don't want to take the entire 2 hours to do that test. We'll see. We'll see what goes on. We'll see what we need to be. But what happens next in chapter 7 is we learn how to do more than just your basic UDU interval. But before we do that, we have to recognize which intervals are UDU intervals, which are the ones that we can't do. So when we start chapter 7 here, we're going to do a review of integrals to see what you know and what you don't know. How's that sound? Do you have any questions before I move on to chapter 7? All good? What time we get out of here? You're noon? Our extra hour day. Folks at home, Jamie, so you doing okay? Any questions, anybody? Nope. So every now and then, some of you tell me that you're a little rusty on your integration. Now's a chance to fix that by practicing lots of problems from section 7.1. What's the interval I wanted to do with it? And there they are. And so in section 7.1, we have some review of basic intervals. So I want to see, I want to write down 3 similar intervals, and then you're going to tell me which ones you know how to do. We can think of 2 of these as basic intervals, and one of them is not. Just a subtle difference in all of them. They're all integrating some version of a sine function. Which of these can you do?
We can do the first one.
You can do the first one. Right, let's see integral of the sine. Will be a negative cosine, right? And 5x means we've got a little substitution action going on here. If you take u to be 5x, the du is 5 times dx, 1/5 du is dx. I've been kind of doing that part in my head when we did integrals like this. Because I knew that I would end up with an integral that looked like 1/5 integral sine of u du. And then again, the integral of the sine of u is minus the cosine of u, where u is 5x. The way that we knew that we could integrate this is we needed this to be a linear function because I didn't have any polynomial terms out here. We had generated a formula to compute sine squared. So we do the same substitution over here. We write that as a sine squared of u du, and then we have our formula for that one. Do I still remember it? It's been a couple sections since we've used it. Sine of 2 things. Oh, I'm skipping that step. I'm doing that integration step already. When I do that integration step, we had the formula that has a sine twice that variable over 4.
Did I say cosine?
We did say cosine. That's like you're doing the identity. And in this case, u was the same as before. Each u is 5x. But this one we can't do. Why not? What's the big difference here? There's still going to be an x over here. If the derivative of this has an x in it, then I would need an x outside of the trig function. So we don't have the du term. So we don't have the skills. We can only integrate the u du integrals. We don't know how to integrate the sine of 5x squared because I don't have an x dx out there. So we're going to be able to recognize that. But you do need to remember that the integral of the sine of u is cosine. All right, so here's my next one. Here's my next integral. Let's see if we go back to this one. Let's go right here. Let's call all of those number 1. Number 2. I think we're probably rustiest with trig functions, so a lot of my examples deal with trig functions. This is the integral of the secant of x times the secant of x plus the tangent of x.
You can do it.
You can do it? I think we can do it without swapping it into sines and cosines. It's not a u du integral though, because if, for instance, u is the secant, what's the derivative of the secant? Forgot that one? Let's write it on the board. I remember it. So we try u du. So the derivative of the secant is secant of x times the tangent of x. I've got plus the tangent of x. So UDU is not gonna work. Doesn't do any good here because then I have to call back view, then I got two terms that I don't have that side. So the next best thing is to multiply it out, and then we'll get it that way. So let's multiply it out. If that didn't work, we can always try sines and cosines. But now when I multiply it out, I see secant squared of x plus secant of x times the tangent of x. I recognize those individually. I know a function whose derivative is secant squared. And I know a function whose derivative is secant times tangent. So I know this integral. Break it up into two separate integrals. Next, the second one I know because of this. If the derivative of a secant is a secant times a tangent, then the integral of a secant times a tangent is just a secant. What function has as its derivative secant squared? It is a tangent. Right? A tangent is secant squared. So the antiderivative of secant squared is the tangent. So there is our antiderivative. So maybe I need to remind you what you know. Right? You know that the integral of the sine of u du is minus the cosine of u. You know that the integral of the cosine of u du is the positive sine of u. You know that the integral of the secant of u times the tangent of u du is the secant of u. The other one we had up here was that the integral of secant squared of u du was the tangent. So the two that I left off was the integral of the cosecant of u times the cotangent of u du. That one was minus the cosecant of u. The one that looks like that one, the integral of the cosecant squared of u is minus the cotangent. 1, 2, 3, 4, 5, 6. Those are the 6 trig integrals we know. Then you can add to that list the integral of the sine squared of u and cosine squared of u that we developed in the last section. What's the integral of e to the u? E to the u. And we don't have let's see, we had something to integrate to get the logarithm. That was the 1 over u. Integral of 1 over u du is the natural log of u. We had 3 rational expressions whose integrals gave us the inverse trig functions. Do you remember what they look like? Which inverse trig function is that one?
You're gonna write it down, we're all gonna remember.
No, it's not sine or cosine, it's inverse tangent. As I'm writing these down, not everybody knew that. The arc sine has a square root and a minus on it. And then the arc secant The arc of cotangent just has a negative numerator. The arc of cosine has a -1 up here. And the arc of cosecant has a -1 there. So we can just pull out the minuses and not have to go the other three trig integrals. These we remember because the tangent represents the ratio of the legs of the triangle, the a squared plus the b squared. The sine represents the opposite over the hypotenuse. So how would you find the hypotenuse? This will be opposite, then the hypotenuse is going to be leg squared minus the other leg squared. So that tells me the minus sign. And then the secant is related to cosine, so that takes the adjacent of the hypotenuse. So we have to swap the order of our leg squares. So that's how I can remember these based upon right triangle trigonometry. Do we have any other integrals that I'm forgetting other than the sine squared and cosine squared? Anyway, the integral of sine squared of u over 2 minus the sine of 2u over 4 plus c, and the integral of cosine squared of u du as a plus in between. We're going to add to this list. We could probably integrate the tangent real easily. Because we could write that in terms of sines and cosines, right? So the tangent of u is going to be the sine of u or the cosine of u, or if we're integrating tangent of x, and then the function on the bottom has the derivative as its derivative on the top. So that turns into a logarithm integral. Since cosine is on the bottom, where my du term is going to have a minus. of that trig function on the bottom, right? Minus the natural log of the cosine of u. Sometimes you'll see the integral of the tangent of u is written as the natural log of the secant of u. Because remember the property of logarithms that takes coefficients and uses them as the power? This could be a coefficient of -1. And so I take the cosine and raise it to the -1 power. Raising something to the -1 power flips it to the denominator. 1 over the cosine is the secant. So however you remember it more easily, you'll see it in both forms throughout this chapter. So that's a simple UDU integral that generates that formula. Now, third example. You don't have a trig function whose derivative is just the secant of x. If I write that as 1 over the cosine of x dx, I still can't integrate it. I was able to integrate a 1 over cosine here because I had a sine in the numerator, so that I could do the UDU substitution. So I don't have that available to me here. But I think back to that other example that when I had a secant times a secant plus a tangent, then I had something I could do. So I'm going to kind of mimic that trick. So watch this trick. I'm going to multiply by 1. That's allowed in every single state, including Arkansas. But I'm going to multiply by 1 using my trig expression. I'm going to multiply top and bottom by the secant of x plus the tangent of x. I'm kind of motivated by what went on in that previous example. I'm going to go ahead and distribute the secant through the numerator. And this becomes secant squared of x plus secant of x times the tangent of x. And downstairs I have the secant of x plus the tangent of x. Now maybe you're kind of seeing why I did that. You're not, maybe you're just writing. What's the derivative of this secant right here? It's that guy. And the derivative of this is that guy. So this multiplied by 1 has given me a u du integral, if u is the denominator. U is secant of x plus the tangent of x, then du secant x tan x plus secant squared of x dx. That's this numerator, just in the other order, but it's just commutative. So this gives me a 1 over u du integral. And that's our logarithm. So the integral of the natural log of the secant of x, is the natural log of the secant of x plus tangent of x. I do that one today because later on in this chapter, we're going to integrate this one so many times. Let's just agree to memorize this as a formula. So let's put it in our list of formulas. That the integral of the secant of u du is the natural log of the secant of u plus the tangent of u plus c. And a similar trick will work for integrating a cosecant. So let's do the integral of the cosecant. By doing the same kind of idea. You mimic all of these steps right here. This is like part B of number 3. Cosecant is 1 over the sine. So again, I can't change it to my more familiar trig functions and have an integral I know how to do. But I do know that I know how to integrate a cosecant squared, and I know how to integrate a cosecant times a cotangent. And so my version of 1 that I want to multiply by is going to have a cosecant plus a cotangent in it. I multiply on top, I have to multiply it on bottom. Same trick. Now I'm going to distribute the cosecant of x through there. So the integral of the cosecant of x was a minus cotangent, which means if I take the derivative of cotangent, I get the minus cosecant squared. The integral of cosecant cotangent was a cosecant, so if I integrate that, I should get that. That means I've got a u du integral. Again, take u to be the denominator. Now take the derivative of those terms. The derivative cosecant of x is a minus cosecant cotangent. The derivative cotangent is a minus cosecant squared. So that's the same as the numerator, but off by a minus sign. So I take that minus sign to the other side, and oops, lost it. And then that integral becomes minus 1 over u du. We get minus the natural log of the opposite value of u, which is minus the natural log of the opposite value of my cosecant of x plus cotangent of x. So over here, I'm going to write that. It's minus the natural log cosecant of x, cosecant of u plus the cotangent of u. Because then we got the plus these and put up our board. They're there. And we may as well write down the integral of the cotangent of u. Can you do that one in your head? You think you get when you integrate cotangent of u, which is cosine over sine. Do it on paper, right? It's cosine over sine du. Anything? Get the natural log of sine. This will be a positive. So we've added 4 more integrals to your list of basic integrals. And that's not even mentioning the extra power rule. What about that one? That one's as common as brushing your teeth. All right, so now I'm going to give you some knockoff version of what we've done. Here's my number 4. Let's see, we want to integrate a fraction that has in its numerator the secant of x times the tangent of x, and has in its denominator 1 plus secant squared of x. So remember, this section is called Review of Basic Integrals. Can you manipulate this into one of your basic integrals? It's not u to u, is it? We chose u to be the denominator. Does it have any chance of having that derivative in the numerator? Because I have to take a derivative of secant squared, get use the power rule, so that's 2 times secant to the first times secant times tangent. It's got too many secants in it. If you try writing it in terms of sines and cosines, sometimes I get a little wonder a bit about, isn't there a Pythagorean identity that relates tangent squared to secant squared? Let's write down our Pythagorean identities. Sine squared plus cosine squared is 1, right? That one everybody knows. If I want to know the other ones, I generate them from that one. So let me start with this equation and rewrite it. I want the one that has the tangent squared in it. I know sine squared over cosine squared is tangent squared. So I'm going to divide each term by cosine squared. So that tells me the other version of this identity is that tangent squared of x plus 1 is equal to, well, there's my secant squared. So does it help to replace this secant squared with tangent squared plus 1? Can you do that? Is that a better integral? Both have the problem that the u on the bottom doesn't give me the du on the top. Good, tangent secant squared. That's not what I have on the top. Same problem up here. I didn't have that. U is equal to 1 plus secant squared of x. Du was 2 secant of x times secant of x, tangent of x. Yes. So I don't really have it there either. So neither one of those tricks work. Dang, I'm fresh out of ideas. I don't know. I don't know where I brought this problem here. I don't know how to do it. Let's try to write terms of sines and cosines. Haven't tried it yet. Let's give it a shot. So let's go back to this one. Replace each thing with sines and cosines. Secant is 1 over cosine. Tangent is sine over cosine. Okay, so I have a cosine squared on top. If you rewrite this now, like sine of x over the cosine squared of x. I'm going to get a common denominator here. I'm going to think of this one as cosine squared over cosine squared. And so I can write my numerator as cosine squared of x plus 1 all over the cosine squared of x. Okay, got a common denominator here. So when I do my flip and multiply term, you'll get the cancellation. That might be helpful. Let's see, none of that works, so let's take that away. But I'm getting fired up when I see that. Does that fire you up, Eddie? Guys. At least getting the cosine squared to cancel.
The negative cosecant.
Huh. Nope, I don't think so. All right, I just did the flip and multiply step. So those cosine squareds are going to cancel. I know how to do that one. So if you're looking at you, I have a variable squared plus 1, but that variable has its derivative in the numerator. Make that integral like that one. By taking u to be the cosine of x. I saw that right here. U to be the cosine of x. Its derivative is a minus sine of x. So we'll just put the minus sign with the du. And we can rewrite that whole integral. Sine of x dx is a minus du. And then the cosine squared becomes u squared. And I still have the plus 1. So there she be. There's my arctangent of u, the minus sign out front. Minus the arctangent of my u is the cosine of x. So the basic integrals, now where u du is a basic integral, but with tricks involved. Try something is the trick. I tried 2 versions of a u du, one before I substituted that out in terms of tangent squared, one after. Neither one of them worked. But I still had more trig substitutions I could try, and I did it, and then it worked. So even though it might not be obvious, some of the things that you should try, I hope are obvious. Right? I know your generation's got the computer right there. You just type in, integrate, blah, blah, blah. The computer shows you what the integral is. But I want to see, the point of this chapter is what are the steps that get you there? What is this Wolfram alpha to do when you get those integrals they're spitting out at you? So I got another version of that one. Let's see. I think this one labeled as number 5. Now I'm going to do 3 integrals for number 5. Now I'm going to do 2 integrals for number 5. Only a subtle difference. That one compared to this one. Same denominator. What help this time is e to the 2x. Similar but different. Yes. It's similar. What's the derivative of e to the 4x? 4e to the 4x. So if you've got e to the 4x in your integral in 2 different positions, then that should be a straightforward u substitution. Right? So for this one, I know the stuff under the radical sign has the main part of its derivative right there. So that's a straight u du substitution. I can write this as 1 over the square root of u du. That's the way we approach here, because they have the same version of e in there. The derivative of e to the power is itself. Times the derivative of power. So that tells me to take the whole stuff inside the radical as the u. I don't know why I have the parentheses there. They're doing nothing for me. Let's go ahead and take those off. And so du Gives you itself times the derivative of the exponent. And put a minus sign on it, so I get the -4 out front. That means I have the -1/4 du. It's going to take the place of my numerator up there. So all this stuff in the numerator is replaced by -1/4 du. Then my denominator becomes the square root of u. Here's the -1/4 du, and there's the square root of u. But I'll write that as u to the -1/2, and I'll get to integrate it with power rule. Add 1 to the power, divide by the new power. Divide by 1/2 puts me at 2 out here. So I get a -1/2 u, which is 1 minus e to the 4x, to the 1/2 plus c. So if you have the same power of e in several places in your integrand, then that's probably a u du integral of some type. But my next example has an e to the 2x in my numerator. So that means I need an e to the 2x in my denominator. But I have an e to the 4x. If I have an e to the 4x, that means I do have an e to the 2x. Because e to the 4x is the same as e to the 2x all squared. So that's what I'm going to do. If I have an e to the 2x up top, then I need an e to the 2x on the bottom. And I have it. I just have to recognize that I have it. And so my u is just going to be this one term right here. Not the whole denominator, just that one term. Because only that one term has its derivative here. I take u to be e to the 2x. So the du is 2 e to the 2x. Put that 2 over there. And now I can replace e to the 2x dx with 1/2 du. And my denominator will look like 1 minus u squared under the square root sign. I got one of those. There's one of those over there. Square root of 1 minus u squared in the denominator is an arc sine. So that's an arc sine integral. It's the arc sine of u. The u is e to the 2x. What we're going to do is generalize these integrals when there's not a 1 here. I have another number here other than a 1. And we get a little manipulation over here. We'll do that next time. And then I've got a handful of other examples still. I've worked through 1 through 5 on a little example sheet. I'm going to post this one on the Blackboard with all of them worked out once we work them all out. So the main part is to practice your integrals. There's a whole bunch of different basic UU substitutions in your book, more so than what I put on my example sheet. And so that you know in subsequent sections what you know how to do in number. The ones you never how to do, that's when you have to start scrambling. So that's it for today, huh? Thank you guys for coming. Thank you guys for attending via Zoom. And thank you especially for filling in. I'm going to call these numbers here and see how to zoom from here with the apparatus. Guys, I was at home. Can you catch you up? Somebody have questions? Okay. There's another